In this lecture, I'm going to discuss equations of planes, and we will also talk about planes and lines at the same time as these objects appear together very often. So, given a plane in 3 dimensions, let's see, what sort of information would I need to generate the plane? First, I need the location in space, so I can prescribe, just like we did before with lines, I can prescribe a point P that passes through the plane, or point through which the plane is going to pass through. And second of all, because through a single point I can draw infinitely many planes in all different directions. So the second thing that I need to prescribe to specify the plane uniquely will be its orientation. And as orientation of a plane, for example, I can choose a direction which is perpendicular to it. So, given a point P and a vector V, I may want to find the equation of the plane through P that is perpendicular to V. So, that's the goal. Find the equation of the plane that contains a point P with coordinates x0, y0, and z0, and the plane is perpendicular to the vector V with components A, B, and C. Okay, so we're going to follow a similar strategy that we used to find equation of a line. So if this is my point P, I can find a position vector for the point P, just like before. I am going to call it R0. Then I can pick an arbitrary point on the same plane and call this point, call a position vector to this point R. And then, just like we did before, I can connect endpoints of the two vectors by a third vector, and it should be easy to convince yourself that this third vector is again R minus R0, right? Because R0 plus this vector will give me R. And then R minus R0 should lie in a plane that I'm looking for, and the plane is perpendicular to the vector V, so in particular any vector that lies within that plane is going to be also perpendicular to V, so this angle should be 90 degrees. So, given any point on the plane with the position vector R, we have that R minus R0 should be orthogonal to V. And then, as we know already, this implies that if I take a dot product of V with R minus R0, this must be 0, scalar 0. Okay, and then we can write this in components. This is the same thing as A, B, C, dot product with X, Y, Z minus X0, Y0, Z0. This is equal 0. This is the same thing as A, B, C, dot product with a vector x minus x0, y minus y0, z minus z0 equal to 0. And then, because the dot product is sum of coordinate-wise products of elements of the two vectors that are involved in the dot product, it follows that a x minus x0 plus b y minus y0 plus c z minus z0 equal to 0, that would also be an equation of the plane, except that the first equation that I wrote is going to be a vector equation of the plane, and the equation in the box is a scalar equation of the plane. Okay, so now notice that here I can distribute A between x minus x0, B between y and y0, etc. So the equation of the scalar equation of the plane can be rewritten as, so ax minus a x0 plus by minus by0 plus cz minus cz0 equal to 0. That's the same thing as ax plus by plus cz, because a, b, c, x0, y0, and z0 are constants. So if on the left I only keep terms that involve variables, then on the right I will move everything that is just a constant. So ax0 plus by0 plus c z0, and I'm going to call that constant d. And so equation of the plane takes form ax plus by plus cz equal to d, and this would be an equation of the plane in the standard form. So if I refer to the equation of a plane in the standard form, this is what I'm talking about. Okay, so a couple of things to note here. First of all, in the equation of a plane, the coefficients of x, y, and z are a, b, and c. And remember that a, b, and c were components of a vector that was perpendicular to my plane. So if I want to find the vector perpendicular to a plane with a given equation, I simply need to read off different values of A, B, and C, and that immediately gives me a vector perpendicular to my plane. Now, how many different planes can there be perpendicular to the same vector? Of course, infinitely many. They're all parallel. If you take a stack of parallel planes in 3D, they're all perpendicular to the same vector. So if they're all perpendicular to the same vector, then the left-hand side of the equation for all these parallel planes will look the same. And the only thing that distinguishes between them is going to be the coefficient d on the right. And indeed, if you look back, the coefficient d is the thing that depends on the coordinates of the point that lie inside my plane on x0, y0, and z0, because the stuff that remains on the left does not have any information about the point itself. So orientation of the plane is given by A, B, C on the left-hand side, and its exact location is specified by D. Okay, let's do a bunch of examples. So example number 1, find the equation of the plane for the origin and perpendicular to V, to the vector V with components 1, -1, 2. And you see immediately that this is essentially trivial. You just remember that the equation of a plane looks like this. So it is A, B, C, in this case, y are 1, -1, and 2. And the plane passes through the origin, so the point P is 0, 0, 0. And so what we have is 1 times x minus 0 minus 1 times y minus 0 plus 2 times z minus 0 equal to 0. And this can be simplified to x minus y plus 2z equals 0. Okay? So that is fairly easy. Example number 2. Find the equation of the plane let's say that passes through the points. So in order for me to specify a plane by using points, as you might recall, I need 3 points. So because to define a line, I would need 2 points. To define a plane I need 3 points. So let's say that the points are P 1, 0, 0, Q with coordinates 0, 1, 0, and R with coordinates 0, 0, 1. So, always a good idea to draw a picture. X, Y, Z. And here are my 3 points. One is here, one is here, and one is there. And so if I look at the part of a plane in the first octant, I see this triangle, but of course the plane continuous behind the axis in our octants. Okay, so what am I going to do if I want to find the equation of this plane? So this is P, this is Q, and this is R. And I need a vector perpendicular to the plane, and I need to know a point on the plane. So I have 3 points, so that means that I want to find the plane, let's say, through P, which is going to have coordinates 1, 0, 0, in the direction or perpendicular to some vector v. So v is a vector perpendicular to my plane, so it can be something like this. And the question is, how do we find v? And we'll use the knowledge that we already gained before. I can take a vector from P to R, so a vector PR, and we discussed that the vector PR I'm going to get by subtracting position vector for R, 0, 0, 1, from a position vector for R, I need to subtract a position vector for P, 1, 0, 0. So this is minus 1, 0, 1. And then I can find the vector PQ in the same way. So PQ is 0, 1, 0, minus 1, 0, 0. And this is minus 1, 1, 0. So PQ and PR lie in my plane that I'm looking for, and V is perpendicular to the plane. So that means that if I take the product, cross product of PR and PQ, then this vector must be perpendicular to the plane, and therefore it can be used in place of V. So let's find what it is. PR cross PQ. This is IJK. Minus 1, 0, 1. Minus 1, 1, 0. And that is I times the determinant 0, 1, 1, 0, mean minus j times determinant minus 1, 1, minus 1, 0, and then plus k times the determinant minus 1, 0, minus 1, 1. And so the first component, or the parameter that multiplies I, is minus 1. The parameter that multiplies j is 0, minus minus 1, plus 1, but there is a minus in front, so there's another minus 1. And then for k, it's minus 1, minus 0, so again minus 1. And so it follows that I can take as v a vector with components -1, -1, -1. Now, notice that there are infinitely many vectors that are perpendicular to my plane, right? So if v is perpendicular to the plane, if I multiply it by any constant, the vector v, it's still going to be perpendicular to the plane. So for example, if -1, -1, -1 is perpendicular to the plane, then so is 1, 1, 1, or 2, 2, 2, or -2, -2, -2. All of these vectors are parallel and can be used in place of v. So v does not have a unique choice. And so therefore, the equation of the plane, I can use this v and the point P, even though I could have used Q or R, it doesn't matter. So equation of a plane is A -1. So A, B, and C are all -1s. So it's -1 x minus P is P has components 1, 0, 0. So x -1 plus B, which is also -1, y minus 0 -1, the third component of V, C, and that is z minus 0. And this should be equal to 0. So that is my equation of the plane. And if I simplify, this is going to be minus x plus 1 minus y minus z equal to 0. And I can move 1 on the other side and then divide by -1. So I get the final equation, x plus y plus z equal to 1. Right? So that would be my equation of a plane. So that's the answer to this question. Okay, so now what about this? For the same example, what if I want to find, so next example, for the plane in the previous example, find the line of intersection with number 1, let's say xy plane. An xy plane, it is clear, is defined by an equation z equal to 0. So how do I find the line of the intersection? So basically, I have two planes. By the way, so in this case, it's obvious that the xy plane has an equation z equal to 0, but also another way to get this equation is going to be as follows. So xy plane passes through the origin. Zero, 0, 0, and is perpendicular to k, a unit vector along the z-axis with components 0, 0, 1. So if I want to find the equation of xy plane, I need to use my equation of a plane. A is 0 times x minus 0 because it's a plane for the origin, plus another 0 times y minus 0 again, the plane is through the origin, plus 1 times z minus 0 equal to 0. And then if I simplify this equation, this is exactly z equal 0 as we could have figured it out immediately in the beginning. Okay, so now I'm looking for the line of the intersection between my two planes. One plane is x plus y plus z equal 0. And the second plane is z equals 0. Okay? All right, so what are we supposed to do? Basically, we can take z equal to 0 and plug that in into the first equation. So if I do so, I'm going to get x plus y equals 0. But x plus y equal to 0 and z equal to 0 I still carry with me. So x plus y equal to 0 I can rewrite as x equal to minus y, z equal to 0. Okay? And now what I see is that this is a symmetric equation of a line of intersection. Right? Because basically points that lie on the line of intersection, they belong to both planes. And so because they belong to both planes, they must satisfy both equations. And that's what we got here. Okay, and so that would be x equal to minus y is equation of a line that intersects my plane on a plane on a plane z equal to 0. And let's check if that actually is going to correspond to the intuition. So for our plane, all intersection with x, y, and z axis were equal to 1, right? So when I look on the line that my plane up here forms at the intersection with xy plane, it's this line in xy plane. So if you look at this picture from above, you will see that this line is exactly the line. Let's see, there's something fishy here. And what is fishy is that I used the wrong equation. Right, the equation was x plus y plus z equal to 1. So this should be equal to 1. And so therefore x plus y is equal to 1. And therefore I can write this as x equal to 1 minus y. And clearly, this equation of this line is that x equal to 1 minus y, or y equal to 1 minus x. It's a line with a slope minus 1 with the intercepts 1 on both x and y axis. All right. The next example. So if this makes sense, the next example is this. Find the equation of the line of intersection between two planes, and let's make them as follows: x minus y plus z equal to 2, 2x plus 3y minus z equal to 1, maybe equal to 6. And so the question is, actually, let's modify it a little bit. Between two planes, like that, if these planes intersect. Because we have to be mindful of the fact that two planes might be parallel, in which case they do not intersect. So the first question then is, do these planes intersect? And how do we decide? If they're parallel, then they have the same orientation, so they must be perpendicular to the same vectors, to the same line of vectors. And so let's call these planes P1 and P2. So from the equation of the plane, as we discussed previously, P1 is perpendicular to a vector with components that are factors in front of x, y, and z. So it's perpendicular to 1, minus 1, 1. P2, likewise, is perpendicular to a vector which consists of factors in front of x, y, and z, and P2. So it's 2, 3, minus 1. So then one vector in this case is not a scalar multiple of another, and so, in fact, let's give these vectors a name. So maybe this is V1, and this would be V2. And so the consequence of that is that V1 is not parallel to V2, right? Because they're not scalar multiple of each other. And so therefore, the planes that are perpendicular to V1 and V2 cannot be parallel. So P1 is not parallel to P2. And if they're not parallel to each other, so then the conclusion is that P1 and P2 intersect. Along a straight line. So now I have to find the equation of that line. And just like in the previous example, so therefore, points on the line are going to lie on both planes, and so their coordinates must satisfy both equations. For P1 and P2. And so equation for line would solve this system of equations. So these are three equations with two equations with three unknowns. So I should be able to prescribe one of these variables in any way I wish, and then determine the other two. So the standard thing to do, for instance, is to, well, actually, let me do this. Let's keep z fixed and then say that let's set z equal to t. If I set z equal to t, and I assume that t is something known, then I can rewrite my equations in the following way. X minus y is equal to 2 minus z, or 2 minus t, and 2x plus 3y is equal to 6 plus z, or 6 plus t. And so I need to solve both of these equations in terms of, for x and y in terms of t. So let me just simplify this. X minus y is 2 minus t. 2x plus 3y is 6 plus t. So I need to solve for x and y. I can, for instance, multiply the first equation by 3 and add the second equation. So if I do that, I'll have 3x. Okay, so let's go down. Multiply the first equation by 3 and add to the second equation. So what that will do, it will cancel y, and you will get 5x plus minus 3y plus 3y, that is 0. Then 2 times 3 is 6, that's 12. And then minus 3t plus t minus 2t. So you're going to get that as a result. And so from here, it will then follow that x is 12 over 5 minus 2/5 t. Okay? So that is x. But also from the first equation, here. I know that y, can solve it for y, so y is equal to x plus t minus 2. And so I can substitute x that I have already found just now. So y is 12/5 minus 2/5 t, that's x, plus t minus 2. So therefore, this is going to be this is going to be 12/5 minus 2, that is 10/5, 2/5, and then minus 2/5 t plus t, that's 3/5 t. Okay, and so then the conclusion is that x is 12/5 minus 2/5 t, y is 2/5 plus 3/5 t, and z from the beginning was set to t. And this is a parametric equation of a line, so I found the line of intersection. One other thing that I can ask you to do, so if I have a parametric equation of a line of intersection, I can also try to find the symmetric equation. For that, I will need to eliminate t. So let's see. So from the first equation, t is equal to 12/5 minus x divided by 2/5. Then, which by the way is the same thing as 12 minus 5x over 2. From the second equation, t is, if I multiply both sides by 5, that's going to be 5y minus 2 divided by 3. And from the third equation, z is the same as t, so t is z. And so my symmetric equation I'm going to get by equating all of these t's, so 12 minus 5x over 2 is equal to 5y minus 2 over 3, and that is equal to z. So this would be symmetric equation of my line. Okay, and then finally here, let's do this example. Given two planes, let's say P1 that looks like x minus y plus z equal to 0, and P2 2x plus y plus 3z equal to 7. Again, answer the following question. If P1 is not parallel to P2, find the angle between P1 and P2. Okay, so is P1 parallel to P2? So P1 is perpendicular to vector 1, minus 1, 1. P2 is perpendicular to vector 2, 1, 3. So clearly these two vectors are not parallel, right? Because 1 is not a scalar multiple of another. And so P1 is not parallel to P2. Okay, so then it is legitimate to look for the angle between them. And let's use the following picture. So if I have a plane P1, then another plane P2 maybe like that. And I want to find the angle between them. So if I look at this thing from a point of view of the line of the intersection. So there's a vector which is perpendicular to the plane P1. So that's V1. There is a vector that is perpendicular to a plane P2. That's V2. And then it's easy to see that the angle between V1 and V2 is the same as the angle between P1 and P2. So the only thing that I need to do is to find the angle between V1 and V2. And V1 and V2 are vectors that are perpendicular to my plane. I already found them. So I need to find an angle between one minus 1, 1 and 2, 1, 3. And we already know how to do that, right? By using a dot product. So cosine of the angle is going to be, so let's give them names, between V1 and V2 is, so the angle is V1 dot V2 divided by the magnitude of V1, magnitude of V2, cosine of the angle. And so I just need to compute all of these quantities. So V1 dot V2 is going to be 1 times 2 minus 1 times 1 plus 1 times 3. And the magnitude of V1 is square root of 1 square plus 1 square plus 1 square, magnitude of V2, square root of 2 square plus 1 square plus 3 square. And so that is 2 plus 3, 5 minus 1, 4 over square root of 3 times square root of 4 plus 9, 13, 14. And so cosine of theta is 4 over square root of 42, right? And so theta itself is arc cosine of 4 over square root of 42. Whatever that is, you can just compute it on a calculator. All right, so this lecture then provided you with equations of planes and connected the stuff that we're doing for planes to what we did for lines. One final comment, as we discussed way in the beginning of the class, whenever I have a curve in 3D, it is given by two equations. Whenever I have a surface, it's given by one equation. And as you saw, equations of planes that are surfaces are a single equation connecting three coordinates. An equation of a line, for example, a symmetric equation of a line, once you eliminate t, is actually two equations in three coordinates, x, y, and z. So everything seems to match. Okay, thank you.